A bridge is a public promise made from calculations, materials, workmanship, and judgment. When that promise fails, the wreckage matters. But the deeper question is whether engineering becomes measurably safer afterward. So this is not a ranking of the deadliest collapses or the most famous footage. We are looking for the bridge failure that most transformed structural engineering practice. The first test is technical surprise. Did the bridge expose a mechanism engineers poorly understood, or did it reveal that familiar rules had simply been ignored? Those are different kinds of failure. The second test is consequence. Human loss counts, but so do changes to codes, inspection, testing, construction control, and the everyday authority to stop unsafe work. The third test is reach. A lesson about one unusual bridge type is important. A lesson that changes how engineers calculate, communicate, supervise, and accept responsibility is broader. 19th century bridge builders were pushing cast iron, wire cables, rail loads, and unprecedented spans faster than theory and testing could always follow. Kretz was real. So was the bill. Later disasters added new enemies: aerodynamic instability, microscopic cracks, corrosion hidden inside connections, and structures with no spare load path when one member failed. Our 6 cases span more than a century. The winner is not the most cinematic, and not the one with the largest death toll. It is the one whose lesson reached furthest across the profession. At number 6 is the D Bridge disaster of 1847. A train crossing near Chester broke through a cast iron girder bridge associated with the celebrated engineer Robert Stephenson. 4 passengers and the locomotive stoker died. Investigators found that the trussed cast iron girders were too brittle for repeated flexing under heavy trains, despite earlier fractures and repairs. The aftermath strengthened similar bridges, encouraged wrought iron and steel, and produced a major inquiry into iron structures. It was an early forensic warning, but not yet a complete professional reset. Number 5 is the Boschchop Bridge at Angers in 1850. During a violent storm, hundreds of French soldiers crossed a suspension bridge already moving under wind and crowd load. The familiar story says marching resonance destroyed it. The evidence is messier. Soldiers had been ordered to break step, while wind-driven motion, overloading, and severely corroded cable anchorages combined. 226 people died. The disaster sharpened concern about dynamic loading and hidden deterioration, but its lesson was divided among several causes and never became one equally clear worldwide system. Number 4 is the Silver Bridge collapse of 1967 between West Virginia and Ohio. Rush hour traffic vanished into the Ohio River when one eye-bar in a suspension chain fractured. The initiating defect was only about 1/10 of an inch deep. The larger problem was structural. A single critical member could fail without a redundant load path to arrest the collapse. 46 people died. Congress responded in the 1968 Federal Aid Highway Act, and federal standards soon defined inspection methods, intervals, and qualifications. Modern American bridge inspection grew directly from this disaster. That is an extraordinary institutional legacy. Silver ranks 4th only because its greatest transformation came after bridges entered service. It changed inspection more decisively than it changed the full design and construction chain. Number 3 is the first Tacoma Narrows Bridge. Opened in 1940, its exceptionally slender deck moved so visibly in ordinary winds that workers gave it a nickname before the famous collapse. On November 7th, the motion changed from vertical waves into violent twisting. The roadway tore apart and fell, producing the most persuasive bridge failure film ever made. No human life was lost. It is often reduced to simple resonance, which is tidy and incomplete. Washington State's technical history gives torsional flutter as the primary explanation, with vortex effects and the deck's own motion feeding the instability. The key is feedback. Once twisting changed the airflow reinforced more twisting. The bridge was not merely being pushed by wind, its movement was helping create the forces that destroyed it. Tacoma made wind tunnel testing and bridge aerodynamics central to long-span design. Future suspension bridges were shaped to let air pass, stiffened against torsion, and tested as aerodynamic systems. It ranks 3rd because the lesson was profound but concentrated. Tacoma revolutionized the relationship between wind and flexible bridges. Our final 2 changed a wider bundle of materials, calculations, supervision, and and public trust. Number 2 is the first Tay Bridge in Scotland. It opened in 1878 as a celebrated railway crossing, immediately increasing passenger and freight traffic across the Firth of Tay. The design had changed during construction. Brick piers gave way to braced cast iron columns, the number of spans fell, and each remaining span became wider. Celebration arrived before the argument was settled. On December 28, 1879, a storm struck as a train entered the bridge. 13 central high girders fell with it. 75 passengers and crew were lost. The inquiry blamed the bridge's design and placed responsibility on Thomas Bush. Weak cast iron components, poor connections and workmanship, altered foundations, and inadequate treatment of wind all sat inside the failure. The replacement was a new double-track bridge built independently of the old one. Even today, the abandoned original piers stand beside it, like physical footnotes no lawyer could redact. Tay also changed the climate around major British bridges. Designs became heavier, wind received more respect, and public confidence had to be rebuilt with steel, redundancy, and visible conservatism. This is the strongest rival: large loss of life, a public inquiry, a famous engineer held responsible, and a new structure that embodied the correction. It misses first place by a narrow but important margin. The GOAT is the Quebec Bridge. At the start of the 20th century, Quebec wanted a direct rail crossing of the St. Croix, Lawrence, and a stronger position in continental trade. The proposed cantilever span was 1,800 feet, longer than any attempted before it. The scale amplified every assumption. Phoenix Bridge Company engineer Peter Slapka produced the design. Theodore Cooper served as consulting engineer, and the owner failed to place an experienced bridge engineer in effective charge on site. The span had grown from 1,600 to 1,800 feet. Allowable compression stresses increased, and the estimated steel weight proved too low. Yet the main members were not fully redesigned for the heavier dead load. That matters because a cantilever under construction must carry its own enormous weight before it carries a single paying train. The bridge was already testing the calculations every time another member was added. Workers and inspectors then saw lower compression cords bending. One measured deflection grew sharply in less than 2 weeks. A foreman stopped work, but authority and information moved more slowly than the steel. On August 29, 1907, the partly built south arm collapsed into the river. 75 of the 86 workers present were killed, including 33 Mohawk ironworkers from Conowick. The Royal Commission did not blame an unknowable new force. It blamed inadequate design, inadequate checking, and the owner's failure to appoint competent chief engineering supervision. The mechanism was technical. The disaster was organizational too. That is where Quebec overtakes Tacoma. Tacoma exposed a frontier in aerodynamics. Quebec showed that even familiar structural principles are useless when calculations, review, field observation, and authority fail to connect. A new board of internationally experienced engineers redesigned the crossing. The replacement used far more steel, introduced a major K-truss application and nickel steel, and followed new research, testing, and closer designer-contractor coordination. Then came the reversal. In 1916, crews lifted a 5,000-ton center span from barges. A support casting in the lifting system failed. The span dropped into the river, and 13 more workers died. This second collapse had a different immediate cause, which makes the story harsher and more revealing. Correcting the original design did not abolish risk. Construction itself remained an engineering system requiring independent control. A replacement center span was successfully raised in 1917. The completed bridge still carries traffic, and its roughly 549-meter cantilever span remains the world's longest of its type. Quebec was not the deadliest bridge disaster, and Silver Bridge produced a cleaner single line to modern inspection law. Its claim is broader: design loads, independent checking, site leadership, warning escalation, construction control, and professional ethics all meet here. A bridge earns trust twice, first on paper, then under load. The Quebec Bridge had to learn both lessons at a terrible price, and that is why it most transformed the practice, meant to prevent the next failure.